There is a flag on the moon that no one has touched in over half a century. It stands in the Descartes Highlands, planted in April of 1972 by the crew of Apollo 16. The fabric is stiffened with wire because there is no wind on the moon to hold a flag open. There is no weather at all. No rain to fade it, no storms to tear it loose. Just silence and sunlight and the slow turning of shadows across a landscape that has not meaningfully changed in 3 billion years. In the summer of 1972, that flag stood alone. The astronauts who planted it were back on Earth, giving interviews, hugging their children, sleeping in their own beds. The next crew, the last crew, though the world didn't fully believe it yet, was still training in Houston, still 4 months away from their launch. And so for one long summer, the moon belonged to no one. 12 sets of footprints, a handful of abandoned machines still humming quietly on battery and plutonium warmth, 3 parked rovers, and that flag. On the 4th of August 1972, at around 6:20 in the morning Universal Time, the sun erupted. Not a small eruption. Not the routine crackle of a star going about its business. This was one of the most violent solar events ever recorded, a flare so powerful, and a cloud of solar matter so fast, that it crossed the 93 million miles between the Sun and the Earth in under 15 hours. That is still, to this day, one of the fastest transits ever measured. The average storm takes 2 or 3 days to make that journey. This one did it before the next sunrise. On Earth, the storm knocked out long-distance telephone lines in the American Midwest. It painted the sky with auroras so far south that people who had never seen the northern lights in their lives stood in their yards and wondered if something was on fire. And off the coast of Vietnam, in the middle of a war, it did something so strange that the United States Navy kept the full story quiet for decades. On the moon, nothing moved. The flag did not stir. But the radiation came down like invisible rain, a flood of high-energy particles striking a surface that has no atmosphere to soften them, no magnetic field to turn them away. Instruments left behind by earlier Apollo crews felt it and recorded it, faithfully radioing the numbers home to a species that had, by pure luck of scheduling, no one standing there to receive them. For months earlier, there had been men on that surface. For months later, there would be men on it again. The storm arrived in the gap. This is the story of that storm, of where it came from, what it did to the Earth, what it would have done to a human body standing on the moon, and how close the Apollo program came, without ever quite knowing it in the moment, to a very different ending. It is a story about the sun, which we think of as gentle because we have only ever known it from behind a shield. It is a story about luck, the kind of luck you only recognize afterward when you line up the dates and feel something cold move through you. So settle in. Get comfortable. There is no rush tonight. We have 2.5 hours and 93 million miles to cross. Let's begin on Earth in the quiet summer of 1972. Chapter 1: The Quiet Summer. To understand how close the storm came, you first have to understand the calendar. So let's set the scene slowly, the way you'd lay out photographs on a table. It is 1972. The Apollo program, the grandest engineering effort in human history, is winding down. Not because it failed, because it succeeded, and success, strangely, is expensive. The race has been won. The budgets are shrinking. What was once a fleet of planned missions stretching to Apollo 20 has been trimmed and trimmed again until only 2 remain: Apollo 16 in the spring and Apollo 17 at the end of the year. After that, the Saturn V rockets, the most powerful machines ever built by human hands, will go to museums and lie on their sides in the grass and be climbed on by children. Apollo 16 flies in April. John Young, Ken Mattingly, and Charlie Duke. They launch on the 16th, and Young and Duke spend 3 days in the lunar highlands, a bright, ancient, mountainous region called Descartes. They drive their rover across slopes older than complex life on Earth. They collect 200 pounds of rocks. They plant the flag we began with. And on April 27th, they splash down in the Pacific and the moon goes quiet again. Now mark that date, April 27th. The moon is empty. In Houston, attention turns to the finale. Apollo 17, Gene Cernan, Ron Evans, and Harrison Schmitt, the first professional geologists to fly to another world. Their launch is set for December. Between April and December stretches a long, hot, ordinary summer. Training runs, simulations, and again. The crew practices in the back rooms and deserts of America, learning their landing site, a valley called Torres Litro, the way you learn the face of someone you love. It's worth lingering in that summer for a moment because the texture of it matters, the sheer ordinariness of the world the storm was about to visit. 1972. The war in Vietnam grinds through its Nixon years, and the mines we'll meet later have just been sown in the harbors of the North. In June, 5 men are arrested breaking into an office complex in Washington called the Watergate. The newspapers give it modest space, a curiosity, a burglary nobody yet knows they are reading the first sentence of a presidency's obituary. Bobby Fischer and Boris Spassky sit down in Reykjavik in July to play chess for the soul of the Cold War. The pocket calculator is a marvel. The microprocessor is months old. The word internet does not exist. Long-distance telephone calls are events. You plan them, you shout a little, you keep them short. And the power grid, the telephone network, the whole electrical nervous system of civilization has been built, top to bottom, by engineers who never once, and why would they, considered the sun a stakeholder. That is the world standing in the storm's path, electrified enough to be vulnerable and innocent enough to have no idea. And Apollo 16 itself deserves more than a sentence, because the men who missed the storm by 99 days had flown a mission worth remembering. It as Young and Duke and the lander drifted apart from Mattingly in the command module, a problem surfaced in the command module's main engine, an oscillation in its backup steering system. For 6 tense hours the landing was on hold, while Houston and the contractors ran the arithmetic of risk. Mission rules said the engine had to be trusted before the lander could be released to descend. They found their answer, cleared the landing, and Young and Duke went down to Descartes a few hours late. A reminder, if the program needed one, of how many separate mercies a moon landing required. On the surface, they had 3 days of the finest field work of the program to date. They drove their rover up the flank of Stone Mountain and looked back across a landscape no human eye had ever surveyed. Duke called the view buggy on the world's oldest beach. They struggled gloriously with the deep drill. Young, at one point, standing in 1/6 gravity with the earth a marble above him, complained with feeling about the flavor of the orange juice in his suit's drink bag. And there is something perfect about that. A man on the moon wrestling with citrus, the sublime and the domestic holding hands. And they deployed, as every crew since Apollo 11 had, their ALSCP station, hauling the instruments out on their carry bar, drilling, leveling, aligning antennas, leaving behind one more nuclear-warmed listening post on the gray plain. Remember that station. In 99 days it will be the closest thing humanity has to a witness. Then they climbed the ladder for the last time, and the moon emptied again, and the summer began. No one is scheduled to be anywhere near the moon in August. There is no reason for anyone to be. In the entire 4 billion-year history of the moon, Human beings have stood on it for a grand total of a few hundred hours, spread across 5 missions. The odds that anything between visits never really figured into anyone's planning. Space was dangerous during a mission. Between missions, space was just space. That assumption is about to be tested, because while NASA is watching its checklists, something else is turning. The sun rotates like the Earth does once every 27 days or so, as seen from here. And as July gives way to August, the sun's rotation is slowly carrying something around its eastern edge and into view of the Earth. A region, a blemish, a tangled knot of magnetism the size of several planets, catalogued by solar astronomers under the unglamorous name McMath 11976. Sunspot regions come and go all the time. Most live quietly and die quietly. This one with mild interest. It was big and it was complicated, and complicated is the word that matters, though we'll get to why a little later. Here is what no one on Earth could know in the first days of August 1972. This one region, in the space of about 10 days, was about to produce one of the most ferocious sequences of solar violence in the recorded history of our star. Flare after flare after flare. And one eruption, one in particular, on August 4th, that would break records which stand half a century later. The timing, when you lay it against the Apollo calendar, is almost theatrical. 99 days after Apollo 16 left the moon. 125 days before Apollo 17 arrived. Almost exactly halfway through the only gap available. If you were writing it as fiction, an editor would tell you to make it less neat. But before we get to the eruption itself, before August 4th, we need to spend some time with the sun. Because the storm makes no sense and the danger makes no sense unless you understand what kind of object our star actually is. Not the friendly yellow circle from children's drawings. The real thing, the engine. So let's leave Earth behind for a while. Let's cross those 93 million miles slowly. The way light does not light makes the trip in 8 minutes, but we're in no hurry, and let's look at the machine at the center of everything. Interlude, the long watch. Before we look closely at the machine itself, it's worth remembering how long we have been watching it. Because the story of August 1972 is also the last chapter of a much older story. 3.5 centuries of humans staring at the sun and slowly, reluctantly, realizing it has moods. People had noticed the spots long before telescopes. Chinese court astronomers recorded dark marks on the sun more than 2,000 years ago, glimpsed through dust storms and haze at sunset, and dutifully logged them as omens. But the modern watch begins around 1610, when the first telescopes were turned sunward. Galileo was among the earliest, and he was characteristically shrewd about the danger. Rather than put his eye to the instrument, he projected the sun's image onto paper and traced the spots day by day. What his tracings showed was heresy twice over. The sun, supposedly the perfect, incorruptible lamp of the heavens, had blemishes. And the blemishes moved day by day across the disk. The sun was rotating. For a while, sunspot watching was a respectable gentleman's pastime across Europe. Then, in the middle of the 17th century, something strange happened. The spots essentially stopped. For roughly 70 years, a period astronomers now call the Maunder minimum, the sun's face went almost blank. Generations of astronomers lived and died, having seen barely a hand in the early 18th century as mysteriously as it had gone, and the episode remains one of the deepest puzzles in solar physics. Proof that our star can, on the scale of a human lifetime, simply change its behavior. The next great discovery came from an amateur, which is one of the most charming facts in the field. Heinrich Schwabe was a German apothecary who took up solar observing in the 1820s for an entirely different reason. He was hunting a hypothetical planet inside Mercury's orbit and hoped to catch it crossing the sun's face. To avoid mistaking a sunspot for his planet, he began meticulously recording every spot he saw. He never found the planet. It doesn't exist. But after 17 years of daily bookkeeping, he noticed something nobody had seen in 2 centuries of casual watching. The number of spots rose and fell in a rhythm, roughly a decade long. He published quietly in 1843 and was largely ignored and then vindicated. The 11-year solar cycle, the heartbeat of the sun, discovered as a byproduct of a failed planet hunt by a man who sold medicines for a living. Once the cycle was known, the watch became organized. Observatories began keeping standardized daily counts. A Swiss astronomer named Rudolf Wolf reconstructed the record backward through old logbooks and gave the world a continuous sunspot number stretching to the 17th century. A data series still maintained today, one of the longest unbroken scientific measurements our species owns. Networks formed. Photography arrived. By the 20th century, dedicated solar observatories, including the McMath-Hulbert Observatory in Michigan, whose catalog would one day assign the number 11,976 to a certain region, photographed the sun every clear day and telegraphed notable activity around the world. And in 1859, as we'll see properly later tonight, Richard Carrington caught the sun in the act itself, the first flare ever witnessed, and the watchers finally understood that the spots were not just weather on the sun. They were weather that could reach across 93 million miles and touch the Earth. So when region 11,976 came around the limb in late July of 1972, it rotated into the view of a watch that had been standing, in one form or another, for 360 years. The watchers saw it. They measured it, sketched it, classified its magnetic complexity, noted it in the daily bulletins. What they could not do, what 3.5 centuries of watching had still not taught anyone to do, was say when it would break or how hard. The watch could observe everything and predict almost nothing. It was, in August 1972, still essentially what it had been in Galileo's study, humans looking at the sun, waiting to see what it did. Now, the machine they were looking at. From 93 million miles away, the sun looks calm. It looks, honestly, like the most reliable thing in existence. It rises, it sets. It has done so every day of your life, every day of every life, without a single missed morning in 4.5 billion years. We built our clocks on it. We built our religions on it. The one thing everyone on Earth has always agreed on is that the sun comes up. Up close, the calm dissolves. The sun is not a solid object. There is nothing to stand on, no surface in the way a planet has a surface. It is an ocean of ionized gas, plasma, 1,300,000 kilometers across, which is a number too large to feel, so try it this way. If the sun were a hollow ball, you could pour roughly 1,300,000 Earths into it. Every second, 600 million tons of hydrogen into helium, and in the process converts around 4 million tons of matter, the weight of a decent mountain, directly into pure energy. Every second. It has been doing this without pause since before the Earth existed. That energy does not leave quietly. It fights its way out. A photon born in the core spins. And this is one of the most beautiful facts in all of astronomy. On the order of 100,000 years or more bouncing through the dense interior before it finally reaches the outer layers and escapes. The light warming your face on a summer afternoon began its journey before the last ice age. Then it crossed the gap to Earth in 8 minutes. But the light is the gentle part. It is the plasma of charged particles, free electrons and stripped nuclei. It is not just a ball of gas. It is a ball of electricity, and moving electricity makes magnetic fields. The entire star is threaded through with magnetic field lines, like currents in an ocean. And here is the crucial, fateful detail. The sun does not rotate all in one piece. The equator spins faster than the poles. Imagine grabbing a ball of string at the middle and twisting, while the top and bottom lag behind. Over months and years, the sun's own rotation winds its magnetic field up like an over-tightened spring. The field lines stretch, tangle, cross, braid themselves into knots, and magnetic fields like springs store energy. The tighter the tangle, the more energy locked inside. Sometimes a knot of tangled field becomes so buoyant, so stressed, that it bobs up through the sun's surface like a bubble rising through water. Where the field punches through, it chokes off the normal churning flow of heat from below. That patch of surface cools, still around 3,500 to 4,000 degrees, but cooler than the 6,000 degrees around it. And cooler means dimmer, and dimmer, against that blinding backdrop, looks black. That is a sunspot, not a hole, not a blemish, a window into a magnetic knot. When you see a sunspot, you are seeing the visible tip of a vast, invisible structure of stressed magnetism, arching up out of the sun and looping back down, holding in a large, complex region the stored energy of billions of nuclear weapons. The spots come and go on a rhythm, roughly 11 years from quiet to stormy and back, as the winding of the field builds and then collapses and reverses. In 1972, the sun was in what astronomers called solar cycle 20, and here is a detail that surprises almost everyone. The cycle had already peaked, back around 1968 and 69. By 1972, the sun was supposed to be calming down, sliding toward its quiet years. But the declining phase of a solar cycle has a treacherous reputation, one that solar physicists know well. The number of storms goes down, but some of the fiercest individual storms in history have come precisely in these supposedly calming years, when a late, huge, complicated region rotates into view like a final argument. The sun, winding down, does not fade politely. It slams doors on the way out. McMath Region 11,976 was exactly that kind of region. Large, magnetically complex, meaning it wasn't a simple pair of north and south poles, but a crowded, contradictory mess of polarities jammed together, field lines forced into configurations they could not comfortably hold. If a simple sunspot pair is a stretched rubber band, Region 11,976 was a drawer full of rubber bands, wound around each other, twisted past their limit, creaking. In the last days of July 1972, the sun's rotation carried that drawer around the edge of the disk and pointed it slowly toward the Earth. Solar astronomers noticed. They always notice big regions. Observatories around the world sketch and photograph the sun every clear day and had done for over a century. Notes were made. The region was active, worth watching. What nobody could do in 1972 was predict. Space weather forecasting barely existed as a discipline. There were no satellites parked between the Earth and Sun to give early warning the way there are today. Humanity's entire warning system consisted of looking at the sun through telescopes and, in effect, waiting to see if the light suddenly changed. If a flare erupted, we would learn about it at the same moment the flash arrived because nothing carries a message faster than light. The sun does not send warnings ahead of its punches. It cannot. The physics forbids it. So picture the situation as the first days of August arrive. On the sun, a monstrous, overwound magnetic tangle turning to face us. On the Earth, a world with almost no forecasting, telephone networks and power grids built with no thought for the sun at all, and a war in Vietnam where thousands of magnetically triggered sea mines float in shallow coastal water. Remember those. They matter later. And on the moon, nobody, empty. 99 days empty. Every piece is on the board now. Before the eruption, though, we need one more chapter of understanding, the most important one. What actually happens when a magnetic knot like 11,976 finally snaps? What is a solar flare, really? What is that cloud the sun throws? Because the storm that missed Apollo was not one weapon. It was three, arriving in sequence. Each faster than the last is slow, light, then particles, then plasma. And the difference between those three is the difference between life and death for a human being on the moon. Let's take the eruption apart, piece by piece, slowly. Chapter 3: Anatomy of an Eruption. Let's slow down and build this carefully, because everything that follows depends on it. Deep in an active region like McMath 11,976, magnetic field lines are being pushed past their limits. The plasma there embedded in keeps churning, keeps twisting, and the field lines, which resist crossing each other, resist breaking, resist letting go, store more and more energy, the way a bent bow stores the energy of the archer's arms. And then, somewhere in the tangle, two field lines pointing in opposite directions are forced together closely enough, and the configuration fails. They break and reconnect into a new, simpler arrangement. Physicists call it magnetic reconnection, which is a calm name for one of the most violent processes in the solar system. Because when the field snaps into its new shape, all that stored energy has to go somewhere, and it goes everywhere at once. Into heat, into light, into motion, into accelerating particles to nearly the speed of light. That release is a solar flare. The numbers involved refuse to sit still in the mind, but let's try. A large flare releases energy comparable to billions of hydrogen bombs, detonated together, in minutes. The plasma at the reconnection site is heated to tens of millions of degrees, several times hotter than the sun's own core. For a little while, one small patch of the sun's atmosphere outshines entire categories of the electromagnetic spectrum, blasting out X-rays and ultraviolet and radio noise. Now here is the structure of the danger. When a great flare erupts facing Earth, three different things leave the sun at three different speeds. Think of them as three riders leaving the same gate. The first rider is light. The flash itself, X-rays, ultraviolet, radio. It travels at the fastest speed the universe allows, and it crosses to Earth in 8 minutes and 20 seconds. There is no warning before it because no warning can outrun it. When it arrives, it slams into the upper atmosphere on the daylit side of Earth, tears electrons off atoms, and thickens the ionosphere, which, among other things, absorbs shortwave radio. Operators call it a radio blackout. For pilots, ships, and in 1972, soldiers, the long-range radio simply fills with silence or static, sometimes for hours. On the moon, with no atmosphere in the way, that same flash arrives raw. The X-rays alone are not the killer, but they are the starting gun, the announcement that the other two riders are on the road. The second rider is the particle storm. In and around the flare, protons and electrons are accelerated to enormous energies, a decent fraction of the speed of light. The fastest of them arrive at Earth within tens of minutes of the flash. This is what scientists call a solar particle event, or a proton storm, and this rider is the one that kills astronauts in every serious study of the problem. These are not waves of energy. They are matter, atomic shrapnel, individual protons moving so fast that each one carries the punch to smash through metal, through plastic, through skin, through the delicate chemistry of a living cell. Earth's magnetic field deflects most of them toward the poles, and our atmosphere, the equivalent shielding of a slab of steel several feet thick, if you stacked it all up, absorbs the rest. Standing on the ground, you are magnificently protected and you feel nothing. Standing on the moon, you have neither shield, no global magnetic field, no air. The proton storm reaches the lunar surface intact, and every square centimeter of ground and anything standing on it is struck over and over for hours or days. The third rider is the slowest and the largest, the coronal mass ejection, the CME. The reconnection doesn't just flash, it often hurls an entire piece of the sun's atmosphere into space, a magnetized cloud of plasma, billions of tons of it, wider than worlds. It's slower than light, slower than the first wave of particles. Typically, it takes 1 to 3 days to cover the distance to Earth. When it arrives, it doesn't harm bodies directly, it harms planets in a sense. It slams into Earth's magnetic field and shakes it, compresses it, tangles with it. And a shaken magnetic field does something Michael Faraday could have told you about in the 1830s. A changing magnetic field induces electric currents in any long conductor it can reach. Telegraph lines, telephone cables, power grids, pipelines. The longer the wire, the bigger the induced current, as if the storm reaches down and plugs the whole grid into an unwanted socket. That's a geomagnetic storm. It is also, incidentally, the mechanism that makes auroras, charged particles, funneled and energized along the shaken field lines, raining into the upper atmosphere and making the air itself glow, green from oxygen, red from oxygen higher up, purples from nitrogen. The most beautiful thing the sky does, and it is a battle damage report. There is one more cruelty in the physics, and it deserves its own quiet minute, because it explains why the engineers could not simply armor their way out of the problem. The obvious answer to radiation is mass. Put more material between the crew and the storm. And mass does work. It is the whole reason Earth's atmosphere protects you, all those tons of air stacked overhead. But in a spacecraft, every kilogram of shielding is a kilogram that must be lifted, and the rocket equation is merciless. Armor the cabin properly against a great proton storm, and the vehicle can no longer go anywhere. The Apollo engineers ran these numbers early and often, and the numbers always said the same thing: meaningful shelter, no mission. Mission, no meaningful shelter. And there is a subtler trap waiting inside the obvious answer, one that feels almost like the universe teasing. When a very fast proton strikes shielding material, it doesn't always just stop. It can shatter the nuclei it hits, spraying out a secondary shower of fragments, neutrons especially, which carry no charge, ignore magnetic tricks, and are unpleasantly good at reaching deep into tissue. Which means a thin to middling layer of the wrong material can, for some radiation, be worse than almost nothing at all. Not thick enough to stop the storm, just thick enough to turn each incoming particle into several. Shielding design is not a wall. It is a chemistry problem, a geometry problem, a compromise negotiated particle by particle. The best practical answer then and now turns out to be almost comically humble: hide behind your own supplies. Water is excellent shielding. Food is decent shielding. The most protected place in a spacecraft is usually the middle of its own pantry. Hold that thought: a crew sheltering inside their groceries, because half a century later it is still essentially the plan. So to gather the riders together, light in 8 minutes, particles in tens of minutes to hours, the great cloud in a day or 3. One more concept, and it's the one that decides whether people die: dose. Radiation harm is cumulative and it is measured. In the American units of the Apollo era, the measure of biological dose was the rem. A few rem, spread over months, is a normal year for a radiation worker. Around 100 rem received quickly and radiation sickness begins. Nausea, vomiting, exhaustion, falling blood counts, as the fast-dividing cells of the body, bone marrow, the lining of the gut take the worst of the damage. Somewhere in the region of 300 to 500 rem, received quickly and untreated, you reach the range where roughly half of the exposed will die. Above that, survival becomes the exception. Hold those numbers loosely. We'll need them in a while, when we finally ask the question the whole night is circling. What would August 1972 have done to a man in a cotton and rubber suit, standing in the open, 250,000 miles from the nearest hospital? But not yet. First, the eruption itself. Because on the 2nd of August 1972, region 11,976 stopped creaking and started to break. Chapter 4, 14 hours. The sequence began on August 2nd. Region 11,976 had rotated fully into view now, a sprawling archipelago of spots big enough to see through smoked glass. Never do that with your eyes, but people did, and had for centuries. On the 2nd, it produced major flares, and the sun's first riders reached Earth on schedule. Radio blackouts rippled across the daylit hemisphere, and the first clouds were on their way outward. Solar observers, sketching and photographing, understood they were watching a heavyweight wake up. On the 3rd, more flares. More ejections. And this detail matters quietly, enormously. The eruptions of the 2nd and 3rd of August swept the road. Each CME that plows outward through the solar wind clears a kind of tunnel behind it, thinner, quieter interplanetary space, with less material to slow down whatever comes next. The sun, without anything resembling intent, was preparing a fast lane. Then came the 4th of August. At around 6:20 in the morning, Universal Time, region 11,976 produced its masterpiece. A flare so intense it saturated instruments, so bright it belongs on the shortlist of the most powerful flares humans have ever recorded. The X-ray flash reached Earth 8 minutes later and hammered the ionosphere. Across the sunlit side of the planet, long-range radio went to pieces. Behind the flash, the sun had thrown the cloud. And because the road had been swept clean by the days before, this CME did not take the usual 2 or 3 days. It made the journey, sun to Earth, 93 million miles in roughly 14.5 hours. Half a century later, that is still the fastest solar storm transit ever recorded. Nothing before it in the instrumental record, and nothing since. Not the great storms of 1989, not the Halloween storms of 2003, not the monster of July 2012, has beaten it. To do it, the cloud had to average an outward speed of well over 2,500 kilometers per second. 10 million kilometers an hour, sustained, for 14 hours, by a piece of the sun's atmosphere the size of many Earths. It arrived that same night, and the Earth rang like a struck bell. The planet's magnetic field, compressed and shaken, induced currents in every long conductor humanity had strung across the ground, and in 1972, North America was crossed by some of the longest conductors ever built. In the American Midwest, AT&T operated a major long-distance telephone artery, a coaxial cable line running through Illinois, connecting the continent's conversations. The storm's induced currents surged through the line's electronics, tripped its safeguards, and knocked the link out of service. Engineers at Bell studied the event afterward with great care. One of the first modern, well-documented cases of the sun personally reaching down and switching off a piece of the telephone network. Power grids across the continent groaned too, Transformers heated, voltages swung, operators watched their boards do things the manuals didn't cover. The grid of 1972 was smaller and lumpier than today's, and it held. Note the phrasing. It held that time, and the sky put on the show it always does when the field is wounded. Auroras poured south, far out of their Arctic home, seen across the mainland United States and reported from unusually low latitudes, glowing red and green over towns where nobody alive had seen the like. It's worth pausing on what that means. An aurora over low latitudes is not a bigger version of a pretty thing. It is a signature, the sign that the storm has pushed the planet's protective field far, far out of its normal shape. For the general public, that was the story. Radios crackled, some phone calls dropped, the sky glowed strangely, newspapers ran a few curious paragraphs. Within days, life moved on. 1972 was a loud year. A light show barely made the front page. But in two places, the 4th of August 1972 was not a curiosity at all. One of those places was the coast of North Vietnam, where the United States Navy was about to spend several confused hours watching its own weapons go off with no enemy in sight. And the other was a gray, silent, airless plane 250,000 miles away, where the storm's second rider, the proton flood, was arriving with nothing whatsoever standing in its way, and no one standing in its path. We'll take the Navy first. The moon can wait a little longer, it's good at that. Chapter 5, The Navy's Secret. In August of 1972, the war in Vietnam was in its Nixon phase, winding toward negotiation, but violently. That spring, as part of the effort to choke off supplies to the north, the United States had done something it had long threatened. It mined the harbors and coastal waters of North Vietnam. Operation Pocket Money. Thousands upon thousands of sea mines, sown by aircraft into the shallow approaches of Haiphong and the lesser ports, lying in the warm, silty water, waiting. These were not the spiked iron spheres of old war movies. Most were a family of weapon called the Destructor, an ordinary aircraft bomb converted with a clever fuse into a modern influence mine. Influence in mine warfare means the weapon doesn't need to be touched. It listens. Specifically, most of these listen for magnetism. The fuse held a sensor, a magnetometer, that watched the local magnetic field of the Earth. A steel ship is a moving magnetic disturbance. When a hull passed close enough, the field around the mine shifted, the fuse noticed the change, and the bomb fired. Simple, patient, and effective, the mines had shut the port of Haiphong tight all summer. Now bring the two halves of the story together because you can already see it coming, and there's a certain pleasure in watching it arrive. A magnetic influence mine is a machine whose entire understanding of the world is this. The Earth's magnetic field is steady, and only a ship can change it. On the night of August 4th, 1972, the Earth's magnetic field was anything but steady. The fastest solar storm ever recorded was wrapped around the planet, and the field over the Gulf of Tonkin was lurching and swinging in a way no mine designer had ever put in the manual. Off the coast near Han La, aircrews from the carrier Task Force offshore were flying routine patrol over the mined waters when the sea below them began to explode. Dozens of detonations, blooming out of empty water, in a span of time so short it made no tactical sense. No ships, no minesweepers, no enemy activity at all. Just the ocean erupting mine after mine after mine as if the water itself had decided the war was taking too long. You can imagine the sequence of reactions on those aircraft and back on the carrier because they are the reactions anyone would have. First, something triggered them. Second, what could possibly trigger hundreds of square meters of minefield at once? Sabotage, some new Soviet countermeasure. A technical fault rippling through an entire weapon family. which would be its own kind of catastrophe, because the same fuses were deployed across the theater. The Navy took it seriously and investigated with real urgency. And the trail, once followed honestly, led somewhere no naval investigation had ever gone before. The mines had worked exactly as designed. Their magnetometers had sensed a large, fast change in the local magnetic field, and they had fired. The change simply hadn't come from a ship. It had come from the star at the center of the solar system. The investigators consulted the scientific community, including space environment specialists, and the picture assembled itself. The great flare of August 4th, the record-breaking cloud, the violent geomagnetic storm measured worldwide that same night. The conclusion, remarkable then and still remarkable now, was that the sun had swept a minefield. The estimates that emerged from the episode suggested the storm may have fired off a large fraction of the magnetic mines laid along that coast. The detonations actually witnessed near Hun La were only the ones that happened under friendly eyes. For decades, this stayed where wartime engineering embarrassments tend to stay, in classified reports and the memories of the people involved. It surfaced fully only much later, when researchers digging through declassified Navy documents reconstructed the episode and published it, giving the August 1972 storm its strange second life in the histories. The space weather event that intervened in a war. It's worth sitting with this for a moment in the dark because it is the whole theme of tonight in miniature. Human beings build machines around assumptions so deep we don't know we're making them. The field is steady. The grid is isolated. The sky is empty. And the sun, roughly once a generation, files a correction. The mines, at least, had the decency to explain themselves loudly. The storm's other target that week said nothing at all. It just sat there in the sky over Vietnam, over Illinois, over Houston, pale, quiet, keeping its own counsel the way it has for 4 billion years. It's time. Let's go to the moon. On the lunar surface for a while. August 4th, 1972. We can do this safely, you and I, because we're made of words tonight. It is lunar daytime in the western regions, and the landscape is doing what it always does, which is nothing. The sky is black despite the sunshine, because there is no air to scatter light into blue. The ground is the color of wet ash, though it has never been wet. Shadows are knife-edged. The horizon is close. The moon is a small world, and it curves away from you quickly. The silence is not the silence of a quiet room. It is the silence of a place where sound has never existed. There is no medium to carry it. The sun hangs in that black sky looking almost exactly as it looks from a beach on Earth. A little harsher, a little whiter. And on this particular day, if your eyes could see just slightly differently, into the ultraviolet, into X-ray, you would fall to your knees because the sun is screaming. Stay out here a little longer. The moon rewards patience, and there is more to feel before the particles arrive in earnest. Notice, first, what the sunlight is doing to the ground. Lunar daytime is 2 weeks long. The moon turns so slowly that a single day-night cycle takes an Earth month, and by local noon, the surface has been under unfiltered sunshine for the better part of a week. The regolith at your feet has climbed past the boiling point of water. Step into the shadow of a boulder, and the temperature falls within a stride by more than 200 degrees. Not because a breeze carries the heat away, for there is no breeze and nothing to carry, but because in vacuum the only heat that reaches you is the light itself. Sun and shadow are not weather here. They are different worlds, a footstep apart. Notice, too, that there is a kind of atmosphere after all, just not one that helps. The moon holds a whisper of an exosphere, a scattering of atoms so sparse that they never collide with one another, and above the sunlit ground floats a faint haze of electrically charged dust, individual grains lofted by static, by the constant push of sunlight itself. Some of the Apollo crews, orbiting into lunar sunrise, sketched strange glows and streamers along the horizon that may have been exactly this: the moon's ghost of a sky, a few grains thick. It is the closest thing this world has to a veil. Against what is coming, it is nothing at all. And that is the deepest strangeness of standing here during the storm. Every instinct you own is calibrated to a planet that announces its dangers. Wind rises before the squall. Skies darken. Pressure drops and animals go quiet. 4 billion years of Earth evolution wired you to read an atmosphere, and the moon has none to read. The most violent radiation weather of the space age is arriving right now, at this minute of our imagined afternoon, and the only honest report your senses can file is sunny, still, silent, perfect. The dosimeter clipped to a suit is not a convenience here. It is a sixth sense, the only one that works. The proton storm is arriving. You cannot see it, and this is the part that the human mind genuinely struggles to hold. The deadliest weather in the solar system is perfectly invisible. No cloud, no wind, there is nothing to blow. No sound, there is nothing to carry it. The dust at your feet does not stir. The flag, we are not far from a flag, does not move. And yet every second, every square meter of this ground is being struck by a hail of protons carrying energies our bodies never evolved to survive. Because our bodies evolved at the bottom of an ocean of air, behind a magnetic shield, on a planet that has been quietly absorbing this violence on our behalf forever. Let's do what the particles do. Let's follow one in. A single proton thrown out of the reconnection zone above region 11,976 crosses the void in under an hour and arrives at the moon moving at a substantial fraction of the speed of light. It strikes, let's say, the fabric of a spacesuit. The suit's layers are cloth, rubber, aluminized film, superb against vacuum, against heat, against micrometeorite dust. Against a relativistic proton, they are fog. It passes through. It passes through the skin beneath. And now it is traveling through living tissue, and it begins to spend its energy the way a bullet spends momentum, by tearing. Its path through the body is a track of ionization. Molecules with electrons ripped away, chemical bonds snapped, water molecules split into aggressive fragments that go on to do their own damage. When the track crosses a cell nucleus, it can shatter the DNA strands directly, not the subtle single-letter typos the body repairs 1,000 times a day, but double-strand breaks, chromosomes cut through, the blueprint itself severed. One proton does this. The storm delivers trillions. And here the story offers one of its strangest, most intimate details, because astronauts did not need instruments to know these particles existed. They could see them, with their eyes closed. It began on Apollo 11 on the way to the moon when Buzz Aldrin mentioned something odd. In the darkened cabin, eyes shut, trying to sleep, he kept seeing faint flashes of light. Streaks, points, little starbursts that weren't there. The crews that followed confirmed it, settle into the dark, wait a few minutes, and the show begins. A pale flash every minute or three, sometimes a dot, sometimes a line drawn instantly across the private darkness behind your eyelids. The explanation is as beautiful as it is unsettling. The flashes were cosmic ray nuclei, heavy, fast particles from the sun and the deeper galaxy, passing through the astronauts' heads. When one of them crossed the retina, or the fluid of the eye, it deposited a fine thread of energy, and the visual system, which has only one way to report anything, reported it as light. The men were not imagining flashes. They were watching. from the inside individual particles of the environment we've been describing all night, single atoms of the storm country, punching through the one instrument that could feel them and file a report, the human eye. NASA, being NASA, turned it into an experiment. On the last missions, including Apollo 16, whose crew had left the moon 99 days before our storm, astronauts wore a device over their heads in dedicated sessions, a detector helmet lined with particle track emulsion, so that when a flash was called out, the passing nucleus would leave a physical scratch in the plates to be matched against the report. The particles were real, countable, and constant, even in quiet conditions, several an hour through each man's skull. Now scale it. Those flashes were the background, the ordinary drizzle of deep space on a calm day. The August 1972 event raised the particle flux by factors of thousands upon thousands. A crew caught in it would not have needed a single instrument to know the storm had arrived. They would have closed their eyes against the fear and found the storm waiting there too, the darkness itself flickering, dense with streaks, the inside of the skull lit like weather. The body's response has a grim and through atrocities, gave medicine far too much data on acute radiation exposure. The cells that die first are the ones that divide fastest. The bone marrow, which is a factory that never stops, making the blood cells that clot your wounds and fight your infections. The lining of the gut, which replaces itself every few days. Radiation sickness is what it feels like when those factories go dark. First nausea and vomiting within hours if the dose is high. Then a deceptive pause, sometimes a day or two of feeling almost normal, while the blood counts quietly fall. Then the crash, infections the body cannot fight, bleeding it cannot stop, exhaustion at the level of the cell. Whether you live depends overwhelmingly on the number we met earlier, the dose. And so the question of August 1972, the question NASA's radiation specialists sat down to answer very carefully in the months and years afterward, becomes brutally specific. If a man had been standing on the lunar surface, in a suit, during the great event of August 4th, what dose? The analyses done since, and this storm has been analyzed as much as any solar event in history, precisely because of what it almost was, converge on an answer with a chilling shape. Out on the surface, protected only by a suit, an astronaut caught in the peak of the August 1972 particle event would plausibly have absorbed a dose in the range of several hundred rem. Recall the ranges. 100 rem and you are sick. 300 to 500 untreated and survival becomes a coin flip. The treatment in question, transfusions, isolation wards, intensive supportive care being 250,000 miles and a fiery reentry away. Inside the lunar module, the numbers improve, but not to safety. The LM's walls were famously, deliberately thin, in places, the thickness of a few sheets of foil, because every kilogram had been shaved to make the landing possible. Call it partial shelter. Inside the command module, orbiting overhead or cruising between worlds, the shielding was better. A heavier hull, equipment racks, consumables, and the estimated doses dropped to tens of rem. Almost certainly survivable, likely without even acute symptoms, though with a lifetime cancer risk quietly raised and a mission in ruins. So the storm draws a map with 3 zones. On the surface, in a suit, potentially lethal. In the lander, gravely dangerous. In the command module, sick or scared or merely irradiated but probably alive. And here is the detail that makes the whole thing shiver. An Apollo lunar mission by design spent its most important days moving through exactly the wrong zones. Days in transit. Days in orbit. And at the center of the itinerary, men on the surface for up to 3 days in suits in the open, hours at a stretch, with a lander built of foil to run back to. The August storm did not need to be aimed. It only needed an audience. In August 1972, the audience was machines. The ALSCP science stations left behind by earlier crews, nuclear-powered, patient, still faithfully transmitting, felt the storm wash over them and recorded it, clean, beautiful data about a catastrophe that wasn't, sent home to a species that had stepped out of the theater between acts. Which brings us, at last, to the people. The ones who had just left and the ones who were next in line. It's time to talk about the men who weren't there, and about how the near miss looked from inside the program that had, without knowing it, just rolled the luckiest dice of the space age. Interlude: the bet. Before we meet the men on either side of the gap, you need to understand the bet the program had made. Because Apollo did not fly blind into the radiation problem. It flew informed, calculating, and this is the uncomfortable, admirable truth, knowingly. The story starts with the very first American satellite. When Explorer 1 went up in 1958, its Geiger counter returned readings so strange that the physicist behind it, James Van Allen, initially suspected the instrument had failed. At certain altitudes, the counts went off the scale, then to zero, because the detector was being saturated. The Earth, it turned out, is wrapped in belts of trapped radiation, charged particles caught in the planet's magnetic field like flies in amber, forming vast, invisible donuts of hazard around the world. They were named the Van Allen at the Holgate. Trajectory was shaped to cross the belts quickly and through their thinner regions, and the crews carried dosimeters to check the arithmetic. The arithmetic held beautifully. Belt passage cost each astronaut only a small fraction of the dose limits, roughly comparable to a course of medical X-rays. The belts, feared in the 50s as a possible wall around the Earth, turned out to be a toll, not a wall. Solar flares were a different kind of problem entirely, and everyone involved knew it. A great particle event could not be shielded against by any reasonable spacecraft. The mass required would have grounded the Saturn V, and it could not be predicted. So NASA did what engineers do with a risk that can be neither eliminated nor foreseen. It measured it, bounded it, and bought it. The program built a radiation monitoring operation into mission control, a room of specialists whose entire job was the space environment. Solar Patrol telescopes and monitoring stations around the world fed them. Every crew carried passive dosimeters. Flight rules defined what dose readings would trigger what response, up to and including abandoning a lunar landing. If a flare erupted mid-mission, Houston would know within minutes, would watch the particle counts climb in near real time, and would order the crew into the most sheltered configuration available, which, as we've seen, was shelter in name more than substance for men on the surface. And then there was the actuarial layer, the coldest and most honest one. Mission planners studied the statistics of great flares across the solar cycle and computed the odds of a killing storm overlapping a mission. The numbers came out reassuring in exactly the way casino odds are reassuring. Any single mission was very unlikely to be hit. A famous piece of internal arithmetic held that a truly dangerous event during a given 2-week lunar mission was a low single-digit % affair. Fly 9 crewed lunar missions, and the compound risk grows but stays comfortably in the range where the other risks of the Enterprise. The engines, the reentry, the 10,000 single points of failure loomed larger. Radiation was, on paper, roughly the 7th or 8th most likely thing to kill an Apollo crew. The bet stated plainly, great storms are rare, missions are short, and the calendar is wide. We accept a small chance of catastrophe as the price of going. It was a rational bet made by serious people with the best data of the age, and it's worth defending. Every alternative was worse. Waiting for forecasting that could predict flares meant waiting forever. That forecasting does not exist even now. Armoring the spacecraft meant not going. The only way to the moon was through the storm's territory, on the storm's schedule, trusting the gaps. 9 crewed lunar missions flew through those gaps. 24 men crossed the belts and the open country beyond. The sun stayed quiet for Apollo 8's Christmas, for the landing in July of 1969, for the crisis of 13, for all of it, every mission threading the calendar without ever quite knowing it was threading anything. And then, in the 99-day pause after the 8th crossing, the sun played the hand the planners had always known it held. The bet was never wrong, the odds were always real. August 1972 was simply the other column of the ledger, the one that shows what unlikely actually looks like when it stands up, crosses the room, and misses. Now, the men. Chapter 7, The Men Who Weren't There. 99 days before the storm, Charlie Duke was lying in the gray dust of the Descartes Highlands, laughing. He and John Young had been doing what astronauts on the moon actually did much of the time, which was field work, hammering core tubes, bagging rocks, reading the land, and doing it with the giddiness of men who knew exactly how few human beings would ever get to feel 1/6 gravity in their bones. Young jumped and saluted for the camera. Duke left a photograph of his family on the surface, sealed in plastic, where it presumably lies to this day, bleached by half a century of unfiltered sunlight. On April 24th, their lander lifted off the surface. On the 27th, they were bobbing in the Pacific. They spent early August 1972 on Earth, in the ordinary paradise of home, debriefings, family, the slow return of muscles to a full-weight world. When the sky over parts of America glowed with aurora that week, they were under it, not above it, protected by the same blanket of air and magnetism as every other human being alive. The storm, for them, arrived exactly 1 mission too late. For 3 other men, it arrived exactly 1 mission too early. Gene Cernan, Ron Evans, and Harrison Schmitt spent that week deep in training for Apollo 17. Their December mission was to be the program's crescendo, the longest stay, the most science, a professional geologist finally on the surface, a valley Taurus Littrow chosen precisely because it was dramatic, ringed by mountains, threaded by an ancient landslide. 3 days on the surface were planned, over 22 hours of moonwalks. Long rover traverses far from the lander at the farthest points, kilometers away from even the foil-walled shelter of the LM. Run the counterfactual gently, no need for melodrama. The facts carry their own weight. Take the mission as designed and slide the calendar so that the first week of August falls during those 3 surface days. The X-ray flash arrives with no warning. It cannot come with warning, and behind it, within the hour, the proton flood begins. 2 men are out on a traverse. The rover's best speed is a brisk jog. The dosimeters they carry begin to climb, and Houston, which is receiving the same space environment data, patchy and slow by modern standards, has to make the worst call in the program's history with numbers arriving minutes stale. Even in the best version, an immediate scramble back, an emergency ascent, a rendezvous, the storm shortening but not sparing. The crew takes doses somewhere between grave illness and the edge of survivability, and takes them days away from a hospital. In the worst version, the one where the traverse is long and the peak is early, Apollo, a program that had brought every crew home alive from the most dangerous act in human history. into its finest hour, ends with the thing it had always just barely avoided. NASA knew all this. That's an important part of the story, and it's often told wrong, so let's be fair to the people involved. The radiation risk of solar flares was not a blind spot. The agency had a space radiation analysis group. Solar observatories fed the program. Flight rules existed for particle events. The mission planners understood that a great flare during a lunar stay was among the gravest scenarios on the books. What they also understood and said, with the clear-eyed arithmetic of the era, was that the risk could be measured but not scheduled around. Great flares cannot be forecast weeks ahead, not then, not now. Missions could avoid the calendar, could dodge a specific storm. So Apollo flew. Big flares are rare, missions are short, the overlap is unlikely. A few percent of unavoidable program-level risk, accepted with open eyes. It was a rational bet. And in August 1972, 4 months after one crew and 4 months before another, the other side of the bet showed its hand. It's worth knowing who these three were, because history has a way of flattening crews into a mission number. Gene Cernan had flown twice already, had, on Gemini 9, fought a spacesuit soaked in his own sweat through the hardest spacewalk of the early era, and on Apollo 10 had flown the lunar module to within 9 miles of the surface, and then, by design and with what discipline one can only imagine, come home without landing. Ron Evans was the command module pilot, the one who would keep the ship, a naval aviator who had flown combat missions over the same Vietnamese coast where that August, the sea was about to start exploding on its own. And Harrison Jack Schmitt was the outsider the scientists had fought for, a Harvard-trained geologist, drafted into the astronaut corps precisely so that, before the program ended, at least one set of trained scientific eyes would read the moon in person. Their training that summer was the most intense of the program, because Taurus Littrow was the most ambitious site ever attempted, and because everyone involved knew there would be no second chance to get lunar field geology right. Cernan and Schmitt crawled over volcanic fields in Hawaii and craters in Nevada with sample bags and cameras, rehearsing traverses step by step, while Evans drilled the orbital science he would fly alone above them. Through early August, through the very days our storm was pouring its protons onto the empty highlands 250,000 miles away, they were at it, heads down, checklists in hand, preparing to place themselves, for 3 days that December, in exactly the environment the sun had just demonstrated it could make lethal. If any of them lost sleep over the August event, it did not make it into the record in any prominent way, and that, too, is the culture of the program in a sentence. The odds had been accepted long before. The odds had not changed. One more data point had simply landed in the rare but real column. The mission would fly when the mission was ready. And it did. On December 7th, in the only night launch of the program, Apollo 17 rose out of Florida on a pillar of flame that turned the coastal dark briefly into orange daylight. Witnesses talk about it still. Cernan and Schmitt spent 3 days in the valley, longer on the surface than anyone before them, and drove farther, and brought home more of the moon than any crew ever had. Evans circled above, alone in content, the last of the great solo lunar orbiters. The sun, through all of it, behaved a quiet disk, a benign lamp, the good son of the children's drawings. On December 14th, Cernan followed Schmitt up the ladder, paused, and said his piece about returning with peace and hope, the last words spoken from the surface of another world in the 20th century, and as it turned out, for far longer than that. Then the hatch closed, and the moon was empty again. This time the emptiness held. The sun could take all the swings it liked now. The theater was closed. Inside the program, the event landed hard among the people whose job was exactly this. The August 1972 storm was, for the radiation specialists, the proof by demonstration of the scenario they had been modeling on paper. Not a hypothetical composite, but a real, measured, screaming fast particle event in the precise window of the final missions. It entered the literature almost immediately and never left. To this day, when engineers design radiation shielding for a crewed deep space vehicle, one of the canonical reference cases, the standard nightmare they test the design against, is August 1972. The storm became a unit of measure, a ruler made of luck, and Apollo 17 flew anyway that December because the bet was still the bet. Cernan, Evans, and Schmidt spent their 3 days in Taurus Littrow under a sun that had, by then, gone back to muttering. They came home in mid-December, the last humans, for far longer than anyone that day would have believed, to stand on another world. The sun stayed polite for their entire trip. It had made its point in August to an empty room. Interlude, the machines that felt it. The room was not entirely empty, though. That's the detail worth lingering on before we place this storm among its peers. Because while no human felt August 1972 from the moon was not silent. It was instrumented. Humanity had left machines behind, and the machines were awake. Each Apollo landing crew after the first had spent part of their precious surface time doing something almost domestic, setting up a science station. They called it ALSEP, the Apollo Lunar Surface Experiments Package, and deploying one looked like assembling strange furniture on an ash-gray lawn. A central transmitter station. Instruments carried out on a two-sided rack like water pails and planted at careful distances. Seismometers to feel moonquakes, magnetometers to taste magnetic fields, ion detectors and particle counters to sample whatever arrived from the sky. And at the heart of each station, a small nuclear generator, a cylinder of plutonium-238, warm to the touch through its fins, converting the heat of radioactive decay into a steady trickle of electricity. No sunlight required, no batteries to die in the 2-week lunar night. The stations were built to outlast the visits, and they did by years. In August 1972, there were 4 of these stations alive on the moon, the legacies of Apollo 12, 14, 15, and 16, scattered across thousands of kilometers, from the ocean of storms to the Descartes Highlands, all faithfully radioing their measurements home several times a day to anyone listening. And out in interplanetary space, a small flock of aging Pioneer probes parked in orbits around the sun formed humanity's first crude solar weather picket line, sampling the wind upstream. So when the storm arrived, it walked into a room wired with microphones. The particle detectors at the lunar stations watched the proton flood arrive and climb, clean, continuous measurements of a lethal environment, taken from ground zero, at ground level, exactly where Boots had stood 99 days before. The magnetometers felt the interplanetary field convulse as the great cloud swept past. 250,000 miles away, receivers on Earth wrote it all down. It remains one of the quiet ironies of the space age. Our best surface measurements of the storm that could have killed astronauts on the moon were taken by instruments those astronauts' predecessors had carried out and planted, precisely, so the moon could be studied when no one was there. The data mattered, too. This is not just poetry. The lunar surface and deep space measurements of August 1972 became a reference dataset. They anchored the dose reconstructions we visited earlier, calibrated the models of how solar particles propagate, and gave the shielding engineers of every later program a measured, real, worst-case week to design against. When a modern spacecraft's radiation plan cites the August 1972 event, and they do, half a century on, the citation ultimately traces back, in part, to those little nuclear-warmed stations, dutifully reporting the invisible weather to an empty channel. The stations kept working for years afterward. They felt moonquakes and meteorite strikes and the slow thermal breathing of the lunar day. In September of 1977, with budgets thinning and the receivers on Earth needed elsewhere, NASA sent the shutdown commands, and one by one the transmitters fell silent. The hardware is all still there, of course. Nothing leaves the moon. 4 small monuments of foil and plutonium, standing in the dust among the footprints, the only witnesses to August 1972 who were actually present, now permanently off the record. To feel the true size of what they recorded, it helps to meet the family it belongs to. Chapter 8: The Family of STORMS. To feel the true size of August 1972, it helps to meet the family it belongs to, the small, terrible aristocracy of storms that humanity has actually recorded. There are only a handful of names on the list, and each one teaches a different lesson. Take them slowly, like portraits in a hall. If you are drifting by now, and you are allowed to be, that is the whole arrangement tonight. Here is the story so far folded small. In the summer of 1972, between the 8th and 9th human visits to the moon, a tangled region of the sun produced one of the most violent eruptions ever recorded. Its cloud crossed to Earth faster than any storm before or since. It broke telephone lines in Illinois, lit the sky far south of its usual country, and detonated a minefield in a war zone. And on the moon, where there is no shield of any kind, it delivered a flood of radiation that would have gravely endangered, plausibly killed, anyone standing on the surface. No one was. By 99 days on one side and 125 on the other, no one was. That is the heart of it. Everything else tonight is context, and the context now asks for the family album. The patriarch is Carrington, 1859. On the 1st of September that year, a British astronomer named Richard Carrington was doing what respectable gentlemen scientists did, projecting the sun through a telescope to sketch its spots, when, before his eyes, 2 beads of white light flared inside a great sunspot group, brightened and faded, in about 5 minutes. He had just become the first human being to witness a solar flare. Within a day, the Earth was inside the fiercest geomagnetic storm in the instrumental record. Auroras were seen near the tropics. Miners in the American West reportedly woke and made breakfast at midnight, thinking dawn had come. And the world's only long-distance electrical technology, the telegraph, went mad. Lines sparked, operators reported shocks, some offices caught fire, and most famously of all, some telegraphers disconnected their batteries and found they could keep sending on the storm's own current. The sun ran the telegraph network for a few hours, out of its own pocket. The lesson of Carrington is the simplest and the worst. It can be that big. Estimates place it well beyond anything in the modern instrumental era. It struck a world whose entire electrical nervous system was a few telegraph wires. The same event today would find a civilization that has, in the meantime, wired itself completely. Next portrait, Quebec, March 1989. A large storm nowhere near Carrington's size hit the Hydro-Quebec power grid, whose long lines sat on ancient, poorly conducting rock that made them especially good antennas for storm currents. Protective relays tripped in cascade, and in 90 seconds the entire province went dark. 6 million people on a freezing March night without power for 9 hours. The lesson of 1989. It doesn't take the biggest storm. It takes the right storm meeting the right grid. Utilities across the world quietly rewrote procedures after that one. Then the Halloween storms. late October and early November 2003, a barrage of giant flares in quick succession, spectacle and disruption together. Airline routes shifted away from the poles, astronauts on the young space station sheltering in its most shielded module, satellites damaged, one flare so strong it blinded the very instruments built to measure it. The lesson of 2003. The modern, satellite-dependent world got a live-fire exercise and passed bruised. And then the ghost, July 23, 2012. The one almost nobody outside the field knows and the one that should keep planners awake. On that day, the sun launched a storm that, by the best analyses, sat in Carrington's weight class, through a stretch of sky the Earth had occupied roughly 9 days earlier. It missed. It hit instead a solar observatory spacecraft called Stereoway, which took the blow like a crash-test dummy and radioed home the full measurements of a civilization-scale storm that hit no civilization. The lesson of 2012 is the same lesson as August 1972, restated for a new century. The difference between a historical footnote and a historical dividing line can be a handful of days on a calendar. We live in the gaps, mostly without noticing. Where does August 1972 sit in this hall? It holds two distinctions. It is still the Sprinter, the fastest sun-to-Earth transit ever measured, the record untouched for over 50 years. And it is the only member of the family that took its swing at the precise, narrow, 99-day-wide window in all of human history when people had been walking, and were about to walk again, on a world with no shield at all. Carrington found telegraphs. 1989 found a grid. 2012 found empty space. August 1972 found an empty moon by 4 months. Chapter 9, What We Built Because of IT. Near misses are gifts, if a species is wise enough to unwrap them. So before we return to the flag and let the night wind down, spend a little while on what the August storm and its whole terrible family actually changed. Because a great deal of the quiet machinery protecting this moment, right now as you drift, descends from those 10 days in 1972. Start with the Watchers. In 1972, humanity's solar warning system was, functionally, telescopes and hope. Today, the sun is the most watched object in the sky, around the clock, from multiple directions at once. A spacecraft called SOHO has stared at it continuously since the 90s from a gravitational balance point, a million miles sunward of Earth. The Solar Dynamics Observatory films it in ultraviolet, constantly, in resolution that would have made 1972's astronomers weep. Probes like Parker Solar Probe have flown into the outer corona itself, and Solar Orbiter has climbed out of the ecliptic to photograph the sun's poles, the first eyes ever to see them properly. And crucially, sentinels parked upstream in the solar wind taste every storm before it reaches us, radioing ahead the one thing 1972 never had: minutes to hours of certain, measured warning of what is about to hit the field. It is still not much warning. The flash still arrives unannounced, physics has not changed. But the cloud, the geomagnetic blow, the part that hurts grids and satellites, that we now see coming. It's fair to ask, after all this watching and all this machinery, why can we still not simply predict the flare itself? Half a century of science and the flash still arrives unannounced. Why? The honest answer is that flare prediction is weather forecasting inside a star, using only the view from outside. We can see the sunspots. We can measure the magnetic tangle above them, classify its complexity, note when a region has the delta-class configuration, opposite polarities crowded inside a single penumbra, that produces most great flares. We can say, and forecasters do say, that a region is dangerous, that the odds of a major flare in the next day or two are elevated, 10%, 30%. What no one can say is now. The final failure, the exact moment a stressed magnetic structure crosses from creaking to snapping, depends on details of the field buried beneath the visible surface. In plasma we cannot see through, at scales we cannot resolve. It is the same reason no one can name the minute an earthquake fault will slip. You can map the strain for decades and still be surprised by the afternoon. So the modern system is built, wisely, around the things that can be known, not the moment of the flare but everything after it. Detection in seconds, particle warnings in minutes, cloud arrival forecasts accurate to hours. The strategy is not to outguess the sun. It is to shrink the interval between the sun's move and ours until the interval is survivable. In 1972, that interval for a crew on the moon was effectively the whole storm. Today it is minutes. That is the entire progress of 50 years, and it is enormous, and it is also, in the deepest sense, the same humility Galileo practiced. We still cannot make the sun tell us its plans. We have only gotten very fast at reading its face. Then the forecasters. Space weather is a genuine operational discipline now. Government centers issue watches and warnings the way meteorologists do for hurricanes. Power grid operators receive storm alerts and can, in the worst cases, deliberately reconfigure, reduce load on vulnerable lines, bring reserve transformers online, sacrifice efficiency for survival. Airlines reroute polar flights during proton events, because at high latitude and high altitude the atmosphere's shielding thins. Satellite operators put spacecraft into safe modes before the cloud arrives. None of this existed when Region 11976 opened fire. Nearly all of it exists, in a traceable line of cause and effect, because storms like it demonstrated the bill. And the crews. This is the part of the inheritance with Apollo's fingerprints on it most clearly. Every serious design for keeping humans alive beyond Earth's magnetic shelter now begins from the assumption August 1972 proved. The great storm will come unannounced, and the vehicle must already contain the answer. The space station keeps its most shielded modules as designated shelters, and crews have practiced retreating to them during proton events. The Orion spacecraft, the one that has now carried humans around the moon again, half a century after CERN closed the hatch, was designed with a storm protocol in which the crew builds an improvised shelter in the densest part of the cabin, stacking the vehicle's own stowage around themselves. Supplies as shielding, the ship rearranged into a burrow. Mission planners model every deep space itinerary against reference storms, and one of the reference storms, the named, canonical, worst-case guessed at every design review, is the August 1972 event itself. There is something quietly moving about that. The storm that found the moon empty never got to write itself into history the loud way. Instead, it was written into the margins of every crewed spacecraft since a ghost that attends the safety reviews, half a century old, keeping people alive by having once, harmlessly, demonstrated exactly how it would have killed them. That is what a near miss is for, if you let it be. And what if it happened now, tonight? It's worth playing the tape once, because the contrast is the whole gift of the intervening half-century. Humans have returned to the moon's neighborhood. The program is called Artemis, and its first crew rounded the far side just this past spring. So imagine a surface expedition somewhere in the lunar south, weeks into a stay, and Region 11976's successor, some future tangle with a new catalog number, letting go exactly as its ancestor did. The flash still arrives unannounced. That has not changed and cannot change. No warning outruns light. But within the same minute, the modern watch reacts. The sun-staring satellites see the flare in a dozen wavelengths. Automated systems flag its class and location. the upstream monitors begin timing the particle rise. Within minutes, not hours, not a next morning telegram, the crew has a proton storm warning with numbers attached, and the numbers update continuously. Mission rules, written with August 1972 cited by name in their ancestry, define exactly what happens next. Surface work stops, the walk back begins before the peak, and the crew configures their shelter in the current designs, quite literally rearranging the densest stowage of their vehicle around the sleeping area, building an igloo of supplies, water, and equipment, turning the mass they brought for living into the mass that keeps them living. Do they escape unharmed? Not necessarily. A 1972 class event at full force, catching a crew far from shelter, is still the nightmare scenario, still capable of ending a mission and marking a body. The sun has not been tamed, it has only been put under surveillance. But the difference between then and now is the difference between a storm hitting a coastline with no forecast and the same storm hitting one that has been evacuating for a day. In 1972, an exposed crew's first warning of the invisible flood might have been a dosimeter needle and a voice from Houston already minutes behind events. Today it would be a countdown. That countdown was purchased. Every second of it traces back through 50 years of satellites and models and design reviews to a small set of teaching storms. And the fastest teacher of them all struck in August 1972, when the classroom, by 4 months' grace, happened to be empty. One thing, though, has not changed since 1972, and it is worth saying plainly without alarm here in the calm of the night. The sun still cannot be scheduled. The flash still outruns every warning. Somewhere in the sun's future next decade or next century, there is another August 4th, another July 2012, perhaps another Carrington. The forecast is not if. The forecast has never been if. We are simply better now at living with a star. Chapter 10. The Flag. Come back to the Descartes Highlands one last time. It is late August 1972. The storm is over. Nothing here shows it. That is the strange, dreamlike truth of the whole affair. The most violent solar event of the space age swept across this landscape, and the landscape has nothing to say about it. The flag stands exactly as 2 departed men left it in April. The rover sits where it was parked, keys forever in the ignition, so to speak. The footprints, those famous footprints, hold their crisp edges, as they will for 1,000,000 years because nothing here knows how to erase them. The proton flood came down on all of it, invisibly for hours. It passed through the flag's stiffened fabric, through the rover's seats, through the little sealed photograph of Charlie Duke's family lying face up in the dust, through everything, harming nothing, because nothing here was alive. The radiation that would have torn through marrow and gut found only aluminum and fiberglass and ash-colored stone that has been absorbing the sun's tantrums for 4 billion years and has long since stopped keeping count. The moon took the blow the way it takes everything, silently, indifferently, on our behalf this once. And 250,000 miles away, the species that had left those footprints went about its August. Somewhere in Texas, 3 men rehearsed a December landing. Somewhere in the Midwest, telephone engineers wrote up a very unusual outage. Somewhere over the Gulf of Tonkin, naval officers read a report explaining, with as much composure as the sentence allowed, that the sun had detonated their minefield. Auroras faded from the low latitudes. Newspapers moved on. The great storm of August 1972 folded itself into technical journals and classified annexes, and the long memory of a small community of scientists. And the world, having missed its own near miss, mostly never learned it had been in the theater at all. 4 months, 99 days on one side, 125 on the other. In a program that chose its launch windows by the mechanics of orbits and the politics of budgets, by everything, in other words, except the one variable no one could see, the deadliest event of the era threaded the only gap on the calendar. You can call it luck, and it was. You can call it the odds simply holding, and they did. The planners had always said a direct hit was unlikely, and unlikely things mostly don't happen. Both are true. But lying here at the end of the night, maybe the truest way to hold it is this. We are a species that lives behind shields we did not build and mostly cannot see, a magnetic field, an ocean of air, a scheduling gap, and every so often, something enormous passes close enough to remind us the shields are real and being used. And if you are still awake, barely, at the soft edge of it, let the last image be a wide one. Pull back from the flag. Up past the gray highlands, past the little nuclear stations murmuring their data to no one, until the moon is a coin, and then a fingernail and the earth swings into view beside it. Blue, lit, crowded with sleepers. Between the two worlds, nothing. 250,000 miles of the same vacuum the storm crossed in an afternoon. And beyond them both, the sun, which from this height is revealed as what it always was. Not a lamp in anyone's sky, but the actual center of the whole arrangement, holding 8 worlds in its gravity and all of them, always, inside its weather. Everything in tonight's story happened inside that weather. The telegraph fires of 1859 and the dark province of 1989. The minefield and the phone lines. The flag, the footprints, the little sealed photograph of a family, bleaching. The 3 men training in the desert and the 3 men resting at home, and the 99 days of empty luck between them. All of it inside the atmosphere of a star, because that is where we live, all of us, every night of our lives, inside the far, thin, outermost breath of the sun. Most nights that breath is gentle. Tonight it is gentle. The particles arriving over your roof right now are the ordinary drizzle, caught by the field, absorbed by the air, ushered politely toward the poles to make quiet green light for the far north to sleep under. Some night, not tonight, it will not be gentle, and the watchers will see it leave the sun, and the countdown will start, and the species that once missed its own near miss by 4 months will do what it has learned to do: take shelter, ride it out, and add another storm to the family album. But that is some other night's story. The flag is still there tonight. Stiff-armed, sun-bleached nearly white by now, saluting nothing over a plain of undisturbed footprints. The sun that bleached it is quiet this evening, or as quiet as a furnace converting 4 million tons of itself into light every second ever gets. It will rise on your window in a few hours, 8 minutes old and 100,000 years in the making, the same reliable morning it has always pretended to be. Sleep well beneath it. It has, after all, been keeping this particular secret for over 50 years, and it kept it in the end from everyone except the empty moon, a minefield, and now you.